confer protection against infection or disease on subsequent exposure to a pathogen. To achieve this, the vaccine must contain antigens that are either derived from the pathogen or produced synthetically to represent component of the pathogen. The essential component of the most vaccine is one or more protein antigen that induce immune responses that provide protection. However, polysaccharide antigen can also induce protective immune response and are the basis of vaccines that have been developed to prevent several bacterial infections, such as pneumonia. By a vaccine is measured in clinical trials that relate immune response to the vaccine antigen to clinical endpoints such as prevention of infection, a reduction in disease severity, or a decreased rate of hospitalization. Finding an immune response that is live or non-live, sometimes loosely referred to as inactivated, to distinguish those vaccines that contain attenuated replicating strains of the relevant pathogenic organism from those that contain only component of a pathogen or kill whole organisms. In addition to the traditional live or non-live vaccine, several other platforms have been developed over the past few decades, including viral vector, nucleic acid-based RNA and DNA vaccine, virus-like particles. The distinction between live and non-live vaccine is important. Live vaccine may have the potential to replicate in the uncontrolled manner in the immune-compromised individual, for example, children with some primary immunodeficiencies or individual with HIV infection, those receiving immune suppressive drugs, leading to some restriction to their use. Type of vaccine: live, attenuated, weakened, or inactivated. The license: measles, mumps, rubella, yellow fever, influenza, oral polio, typhoid, Japanese encephalitis, rotavirus, BCG, varicella zoster. First introduced in 1795 as in the form of smallpox, killed whole organism, whole cell babesiosis, polio, influenza, Japanese encephalitis, hepatitis A, rabies. First introduced in 1896 in the form of typhoid, toxoid, diphtheria, and tetanus. First introduced in 1932 the form of diphtheria. Subunit pure field protein, recombinant protein, polysaccharide peptide. In the babesiosis, example, babesiosis, influenza, hepatitis B, meningococcal, pneumococcal, typhoid, hepatitis A. First introduced in 1970, anthrax, virus-like particle, human poliomavirus. First introduced in 1986, outer membrane vesicle, gram-negative bacteria, outer membrane. Group B, meningococcal, first introduced in 1987. Group B, meningococcal, protein polysaccharide conjugate. Haemophilus influenzae type B, pneumococcal, meningococcal, and the typhoid, first introduced in 1987. The formula for Haemophilus influenzae type B. Viral vector in Ebola, first in 2019. Nucleic acid vaccine, SARS-CoV-2, 2020, SARS-CoV-2. Bacterial vectors, experimentally, cell experiment, antigen presenting cell experimental. Different type of vaccine, schematic representation of different type of vaccine against pathogen. By contrast, non-live vaccine pose no risk to immune-compromised individual, although they may not confer protection on those with B cells or combined immune deficiency. Live vaccines are developed so that in an immunocompetent host they replicate sufficiently to produce a strong immune response, but not so much as to cause significant disease manifestation. For example, the vaccine for measles, mumps, rubella, rotavirus, oral polio vaccine, Mycobacterium bovis, Bacillus calmette, Jurien BCG vaccine for TB, and influenza vaccine live attenuated. There is a trade-off between enough replication of the vaccine pathogen to induce a strong immune response and sufficient attenuation and sufficient. There is a trade-off between enough replication of the vaccine pathogen to induce strong immune response and sufficient attenuation of the pathogen to avoid symptomatic disease. For this reason, some safe live attenuated vaccine require multiple doses and induce relatively short-lived immunity. For example, the live attenuated typhoid vaccine, the other live attenuated vaccine may induce some mild disease. For example, about 5% of children will develop a rash and up to 15% fever after measles vaccination. The antigen component of non-live vaccine can be kill the whole organism. For example, whole cell pertussis vaccine and inactivated polio vaccine purify protein from the organism. For example, acellular pertussis vaccine, recombinant protein, for example, hepatitis B virus. Polysaccharide, for example, pneumococcal vaccine against S. pneumoniae. Toxoid vaccine. Toxoid vaccine, for example, tetanus and diphtheria, are formaldehyde inactivated protein toxin that have been purified for the pathogen. Non-live vaccines are often combined with an adjuvant to improve their ability to induce an immune response. Immunogenicity. There are only few adjuvants that are used routinely in licensed vaccine. However, the portfolio of adjuvant is steadily expanded, with liposome-based adjuvant and oil in water emulsion being licensed in the past few decades. The mechanism of action of aluminum salt, also extensively used as an adjuvant for more than 80 years, remain incompletely understood, but there is increasing evidence that immune response and protection can be enhanced by addition of newer adjuvants that provide leisure signals to the innate immune system. Examples of this novel adjuvant are the oil in water emulsion MF59, which is used in influenza vaccine, AS01, which is used in one of the Shingles vaccine and licensed malaria vaccine, and AS04, which is used in the vaccine against human papillomavirus. Vaccine contain other components that function as preservative emulsifiers such as polysorbate 80 or stabilizer, for example, gelatin or sorbitol. Various products used in the manufacture of vaccine should be theoretically also be carried over to the final product and are used as potential trace component of the vaccine, including antibiotic, egg or yeast protein, latex, formaldehyde, glutaraldehyde, acidity regulator such as potassium or sodium salt. Except in the case of allergy to any of these components, there is no evidence of risk to human health from these trace components of some vaccine. Correlate of protection. The identification of correlate of protection is helpful in vaccine development, as they can be used to compare products and to predict whether the use of an efficacious vaccine in new population. For example, different age group, medical background, geographic location is likely to provide the same protection as observed in the original setting. There is considerable confusion in the literature about the definition of correlate of protection. For the purpose of the discussion, it's useful to separate out two distinct meanings. A mechanistic correlate of protection is a specific functional immune mechanism that is believed to confer protection. For example, antitoxin antibodies, which are used by the tetanus toxoid vaccine confer protection directly by neutralizing the activity of the toxin. A non-mechanistic correlate of protection doesn't in itself provide the protection function but has a statistical relationship with the mechanism of protection. An example of non-mechanistic correlate of protection is total IgG antibody level against pneumococci. These IgG antibodies contain the mechanistic correlate thought to be the subset of opsonopathogenistic antibodies, but the mechanism of protection is not being directly measured. Correlate of protection can be measured in clinical trial if there are post-vaccine sera available for the individual who do or don't develop disease, although large-scale serum collection from participants is rarely undertaken in phase 3 clinical efficacy trial. An alternative approach is to estimate the correlate of protection by the extrapolating from serum epidemiological studies in the vaccinated population and relating the data to disease incidence in the population. Human challenge studies have also been used to determine correlate of protection, although the dose of the challenge bacterium and virus and the experimental condition may not relate closely to natural infection, which can limit the utility of these observation vaccine-induced antibodies. The adaptive immune response is mediated by the B cells that produce antibodies, humoral immunity, and by the T cell cellular immunity. All vaccine in routine use except BCG, which is believed to induce D cell response that prevents severe disease, and innate immune response that may inhibit infection, are sought to maintain confer protection through the induction of antibodies. There is considerable supportive evidence that various types of functional antibodies are important in the vaccine-induced protection, and this evidence comes from three main sources: immunodeficiency states, studies of passive protection, and immunological data, the generation of an immune response to a vaccine, immune response following immunization with conventional protein antigen. The sequence measure histocompatibility class 2 peptide vaccine antigen, the CD4 T cells, and the CDS T cells, the T cell help and soluble vaccine antigen. Here the B cells, CDS effectors T cells, CDS memory T cells, and here we find the maturation of the antibody response. A memory of the B cell proliferate, the plasma cell differentiate, and antibodies produced. In the lipoma, the long-lived plasma cells. The vaccine is injected into the muscle, and the protein antigen is taken up by dendritic cells, which are activated through pattern reorganization receptor by danger signals in the adjuvant, and then trafficked to the draining lymph node. Here, the presentation of peptide of the vaccine protein antigen by measure histocompatibility molecule on the dendritic cell activate T cells through their T cell receptor in combination with signal through the B cell receptor and the T cell bright B cell developed in the lymph node. The T cell dependent B cell development result in maturation of the antibody response to increase antibody affinity and use different antibody isotypes. The production of the short-lived plasma cells, which actively secrete antibodies specific for the vaccine protein, used a rapid rise in serum antibody level over the next 2 weeks. Memory B cells are also produced, which mediate memory. Long-lived plasma cells that can continue to produce antibodies for decades travel to reside in the bone marrow. Each CDA memory T cell can proliferate rapidly when they counter a pathogen. CD8 effector T cells are important for the elimination of the infected cells.